Any questions before we get going? All right, so we're going to calculate some determinants. This finally came to us. Okay. So the geometry of a determinant is basically that the first column of the matrix tells you where the first basis vector goes, which is I hat if we're in 2 or 3 dimensional space, or E1 if we're in a higher one, or we can still call I hat E1. The second column is where E2 is sent. The third column is where E3 is sent. The fourth column is where E4 is sent. If we only have 2 of them, then we can graph on the plane -3, -1, and 2, 6. Notice that you go counterclockwise from I hat to J hat, but you go clockwise from A times I hat to A times J hat. Is that clear from the image? Wait. If you're, can you hear us and see the picture if you're connected remotely?
Yes.
Okay. So since this switches the orientation, so from counterclockwise to clockwise, the determinant should be a negative number. And the absolute value of the determinant is going to be the area of this parallelogram. Because I hat and J hat, the parallelogram they form is a square, right? Because its sides and height are both 1. But the area of this parallelogram will be the absolute value of the determinant, and the determinant will be negative because it switches the orientation. Okay? Well, normally we have to find the height, right, of the parallelogram so that we can multiply it by the base, which would be the length of the vector 2, 6, and that involves a bunch of calculus. Okay, so has everybody watched the video on dot products? Okay, well, you should have, because you knew what we were going to talk about today. Does this reminiscent of Physics 1 and Calculus 2? Okay. So the dot product of the two vectors divided by their lengths gives us the cosine of the angle between them. And so we can find the angle between them and then use sine to figure out what the height of that is. Okay, and this is where cross product comes in. And if you haven't watched dot product, you probably haven't watched cross products. And there are 3 videos: dot products, cross products, and the geometry of cross products, or cross products as a linear transformation. And you should watch all 3 of them because it turns out that dot product is a linear transformation. Why? Because it's linear. We're going to talk about it in Chapter 4 and Chapter 5. And because it's linear, it can be represented by a matrix. Of course, that matrix is a 1 by n matrix because it maps an n by 1 vector to a scalar. In 3 dimensions, we have the unit cube with I hat, J hat, and K hat. And if we have a 3 by 3 unit cube, it has a volume of 1. And we could figure out where I hat, J hat, and K hat go from the 3 columns of our 3 by 3 matrix, right? And the volume of that parallelepiped would be our determinant. And if A times I and A times J and A times K still follow the right-hand rule, then the determinant will be positive. But if it switches the orientation, then the determinant will be negative. The fancy term for a parallelepiped is a polytope. Okay, it's the generic term, just like polygon is the generic term. The generic term in 3 dimensions is polytope. Okay? And a parallelepiped can sometimes refer to in textbooks as a parallelotope for that very same reason. Not so often, though. Okay, and this is the time I wanted you to notice that in scalars, you know, back in elementary school when you wrote 2 times 3 using the little times symbol, or you got a little older and you used 2 times 3 with the little center dot, or 6 times 7, and then later, if they were next to each other, like 6x, or 5y, then being adjacent to each other, they all meant multiplication. Multiplication was the same whether it was the little time symbol or the dot or just being next to each other or separated by parens, right? 3 parens inside -2 would be -6. But in vector multiplication, the little time symbol means cross product, the little dot symbol means dot product, and if they're next to each other, it means matrix multiplication. So all three of them mean something completely different. All right, so today what we're going to do is talk about the Laplace expansion of the determinant. And it is one that, for some reason that I do not understand, 3 or 4 people in the class who are probably not sitting in this room at this moment are going to latch onto as the way to calculate a cross product, even if it's a 6 by 6 or a 7 by 7, and, I don't know why. Even though it says, when I give you the question, there's a rubric in Blackboard that explains don't do that, don't use the Laplace expansion. It says a lot more than that. It's very clear, don't do that. And they do it anyway. And get a 0. And then say really nice things about me in the SPTE. Okay. So, when we have a 3 by 3 matrix, if we want to perform the Laplace expansion, and you've heard the mathematician Laplace at some point or another? Okay, yes, it's the same guy. All right. It seems he figured out a fancy way to calculate determinants that didn't use the 10 properties. And this became the way that they taught in the late 20th century. They taught high school kids to calculate determinants. I'm not sure why. I assume it's because then no explanation was necessary. Just use the formula, right? When in reality, you should have just explained. And the first thing we need to explain about the Laplace expansion is vocabulary. This class, we always start with vocabulary, right? And the first one we're going to start with is the cofactor. And in order to find a cofactor, we need the minor. The minor of the element of a matrix is a smaller n by n matrix. So if I have a 3 by 3 matrix, each of the minors is a 2 by 2 matrix. How do we find that 2 by 2 matrix? Well, let's consider the minor of the 4 in the top left-hand corner. The minor for the element in position 1, 1 means you strike out row 1 and column 1 because it's position 1, 1, right? It's in position column 1, so we're going to get rid of column 1. And it's position row 1, so we're going to get rid of row 1. And the 2 by 2 matrix that's left is called its minor, or minor matrix. It is a submatrix. And the minor for 4 in this 3 by 3 matrix is the 2 by 2 matrix with columns -1, 1 and 2, -4. Now, what's interesting about minors is because they're matrices, we use capital letters. But there are 9 of them, 1 for each element of the matrix, so we have to use subscripts to tell you which one it is. So the minor for A11, meaning the element of matrix A in position 1, 1, is capital M sub 1, 1, meaning it's the minor for the element in position 1, 1. Now, that means in an n by n matrix, there are n squared minor submatrices, each one associated with that element of the matrix. So for element Aij, we have minor, capital Mij. And it's an n minus 1 by n minus 1 matrix, so it's square, so it has a determinant. We can calculate the determinant of the minor submatrix. And we have a special function called SGN, which is short for SIGN, called the sign associated with that element. The sign of this, the sign, 1 or minus 1, associated with the element Aij times the determinant of the minor associated with element Aij is called its cofactor, capital Aij. Now our notation is getting really complicated because we have matrix capital A, we have submatrices minors, capital Mij, and now we also have Aij. So we're using the same capital letter as the original matrix, but we're telling you that it's a cofactor because we're giving it subscripts. And the cofactor is a scalar, even though it's a capital A. Now, I don't like using capital A. I have a different notation. But I got to stick with what's in the textbook, okay? I don't want to deviate from the textbook too much. So, what is the definition of the SGN, or sign, associated with element Aij? Well, it's a 1 if I plus j is even, and a negative 1 if I plus j is odd. In other words, it's negative 1 to the I plus j power. And that's not how I remember it. I remember this picture because it's a checkered board. It's a chessboard, right? With red and green squares, where the red squares are plus and the green squares are minuses. Right? It starts with the red square in the top left-hand corner, which is a plus, and every other square is the other color, whether you go along any row or down any column. So the second row has to start with the minus sign, right? Because it's plus, minus going down the column. And then if we follow the second row, it goes minus, plus, minus, plus, minus. This is how I remember the SGN, or the sigmun. That's actually what SGN is short for. Sigmun. S-I-G-M-U-N. No, not Sigmund. No, this means something else. It means 1 if I plus j is even and negative 1 if I plus j is odd. Okay? And the cofactor of element little aij is its sign, its sigmun, times the determinant of its minor. And we can create the cofactor matrix. The cofactor matrix is an n by n matrix that has as each element the cofactor of each of the elements of the original matrix A. Don't worry, we're going to create a cofactor matrix. In fact, let's start right now. Let's create the cofactor matrix of this 3 by 3 matrix. So Windows Shift S. And I can actually write some notes, right? Which I haven't done a lot of in this class, which is kind of unusual. Okay, so how are we going to create the cofactor matrix? Well, we're going to be doing a lot of computations. All right. So the cofactor matrix of A is going to be a 3 by 3 matrix. Okay. If I start with the 4 in the top left-hand corner and remove its row and column, I'm left with the matrix minus 1, 2, 1, negative 4. And I'm going to do some stuff in our head. Okay? What is the determinant of the minor? 2. Because we know how to compute 2 by 2 determinants in our head. Okay, 2. And the sigmun of the element in the top left-hand corner is positive. So I'm going to write positive 2. Oops. I meant to hit that. I didn't do it. Now let's find the sigmun of this 2 right here in position 1, 2. So I want to calculate the cofactor 1, 2. And that's going to be the sign, the sigmun. What is the sigmun of position 1, 2? Negative. Times the determinant. Now I'm going to remove its row and its column. And I'm left with a 2 by 2 matrix. And this 2 by matrix has columns 2, 2 and 2, 4. And so I'm going to get a negative 8 minus 4, or a negative 4. So the cofactor is negative 4.
Isn't that 2, 2, negative 4?
Is it 2 times 4, 8, and 2 times 2? Oh, negative 4. I forgot the minus sign, yeah. Somehow left it behind. So it's negative 8 minus 4, or positive 12. Is that right? So now I have a cofactor. All right. Now let's find the cofactor. Let's continue along this row and find the cofactor of the element in position 1, 3. So another way to write it, cofactor of a 1, 3 is, well, what's this sigma? Plus or minus? Plus. The determinant, now, I remove, it's in row 1, so I remove all of row 1, and it's in column 3, so I remove all of column 3. And I'm left with the 2 by 2 matrix with columns 2, 2, and negative 1, 1. And what's the determinant here? 4. So the cofactor is positive 4. Now we want the cofactor for this one, the position 2, 2. What's the sigma? Plus or minus?
Minus.
Okay. What's the determinant of its minor?
2 negative.
Minus 8 plus 3 is
Negative 5.
negative 5, and minus and minus 5 is plus 5, right? You see that? Okay. What's the sigma for position 2, 2? Positive or negative? Positive. And what is the minor? Is it have columns 4, 2, and negative 3, negative 4? So what's its determinant? Negative 10, and plus a minus 10 is minus 10. Now, we did a lot of mental arithmetic there. Did everybody follow along? No? Okay. So, when we remove row 2, because it's in position 2, 2, and column 2, because it's in position 2, 2, we're left with, for the cofactor of A 2, 2, that is that negative 1 there, we get plus minus plus, so I'm going to go plus minus plus, so a positive, the determinant of its minor. And its minor has columns 4, 2, and negative 3, negative 4.
And every other space, I'm on track, is negative.
That's right. Just like it.
One is always positive, is that
Yeah.
correct?
Yep. The idea to keep in mind is a chessboard, right? With green squares and red squares. And this determinant, which we have decided the cofactor is the positive determinant, is negative 16 plus 6, or negative 10. Now we've got it? Okay. Now we need the cofactor in position 2, 3. What's its sigma? Negative. And if we remove its row and its column, we're left with a submatrix with columns 4, 2, and 2, 1. What's its determinant?
Is that no?
Yeah, 0.
Yeah, it would be 0.
And negative 0 is 0. Okay. Oop. And now what about position 3, 1? What's the sigma? Positive. And if we move its row and column, we're left with a matrix with columns 2, negative 1, and negative 3, 2, and its determinant is?
It's going to be 7, right?
No.
Negative 1.
Negative 1 times negative 3 is 3, and 2 minus 3 is negative 1. Yeah, it's negative 1. Did you say negative 1? Then you were, if you said negative 1, you were absolutely right. Huh?
4 minus 3?
We're in position 3, 1. I'm going to keep backing up here.
Plus
No, I need Y.
4 is plus, minus, okay, the 1, 1 is plus, 2, 1 is minus, 3, 1 is plus. Right?
4 minus 3, 1, right? Which is what I thought in the first place. And positive 1 is 1. I don't know how I got yeah,
Isn't
I
that
do.
spot negative?
No.
Okay, sorry, I was in the wrong spot.
Now position 3, 2. Is the sigma positive or negative? Negative. What's the determinant of its minor? 2. So negative 2. And finally, position 3, 3. What's its sigma?
Awesome.
Positive. And what's the determinant of its minor?
So it's 0.
Yeah, negative 4 plus 4 is 0. And positive 0 is 0. So now we have the cofactor matrix. Are we good? Did we follow all the steps now? We're starting to do this mental arithmetic? Okay. Why would you care about the cofactor matrix? Because it turns out that if A is invertible, meaning it's a square and its determinant is not equal to 0, then the adjunct in some textbooks this is called an adjoint. Unfortunately, adjoint is also used in lots of other places in mathematics. And finally, in the 21st century, we decided to use a different word. But if your book is more than 20 years old, it's going to call it an adjoint. But we decided, about the time that most of you were born, that we needed another word because this was getting too confusing. But older books, like our old textbook, calls it adjoint, but it's really adjunct. What does this textbook call it? Adjoint or adjunct?
Should be in 3-4.
Just go to the back of the book and look at the glossary. It's 3-1, actually. ADJ.
Adjoint.
Yeah, so even this textbook still uses the word adjoint, which just means it's an old textbook. The adjoint, or adjunct, the adjunct of a matrix is the transpose of the cofactor matrix. And you can always compute the cofactor matrix, whether the matrix is singular or not. Even if it's a zero matrix, it has a cofactor matrix. And you can transpose any matrix, even if it's a zero matrix. So the adjunct always exists. You can always create the adjunct matrix. You just have to find out the n squared cofactors and transpose the cofactor matrix. Okay? But if the matrix, and here's another equation you can always use. The determinant of A, oops, wait a minute. I did it wrong. Let's see. A times the adjunct of A equals the determinant of A times the identity. Why can you always write this, even if A is a singular matrix? Because the A and the adjunct always exist, but even if the determinant of A is 0, 0 times the identity matrix is just a zero matrix. There's no division. But what's the formula in the textbook? If I multiply both, if A is invertible, I can multiply both sides of this equation by A inverse and get the adjunct of A equals the determinant of A times A inverse times the identity, which is just A inverse. And if A is invertible, the determinant is not equal to 0, so I can divide both sides by the determinant. And I get A inverse equals 1 over the determinant of A, which might be negative in spite of the fact that we're using vertical bars, times the adjunct. Now, this isn't very useful unless it's a 2 by 2 or a 3 by 3 matrix, and we can do a lot of that arithmetic in our head, right? So if you're on a test and you need the inverse of an invertible 2 by 2 matrix, we're going to use this method. So let's do that.
So this is where we get the formula, I think this is where you derive the formula for matrix inverse, is that it?
That's the one they gave you in the textbook that I didn't use. By the way, you guys all looked at the post and I showed you how to invert the cosine, the one with cosines and sines without using the formula? Yeah, it wasn't necessary. Row operations worked just fine. You just had to be clever about your row operations so that you were conveniently using lots of trig identities, right? Like 1 minus cosine squared is sine squared, things like that. But you didn't need that formula. And to be honest, the committee likes this textbook more than the other textbook, but it doesn't like a few things in it because nobody ever agrees about everything. And this is one of the things they don't like is in the second chapter, they introduced that fancy formula for inverse of a 2 by 2 without giving you chapter 3 to explain what the heck it means. And they also gave you that ridiculous formula for the projection matrix without explaining what the heck it was, and then we're not going to explain it until chapter 5, right? When there was a much easier way to do it, which is the way I showed you in class to solve the same problem, where you multiply both sides by A transpose and then make an augmented matrix and just row operations and solve it. You just didn't need all that. A times the inverse of A transpose A times A transpose, right? Which is the projection matrix. And projection matrices are also similar. That's like the formula we're encroaching on in this class, the Laplace expansion. It's a really complicated, ugly formula that nobody should have to memorize. Okay? There's easier ways to do the problem. Okay, but if you have a 2 by 2, and here's the thing, the textbook, and every textbook I've ever found that teaches introductory linear algebra uses this formula. But you can't use this formula unless you already know the determinant of A is not equal to 0. So if, for example, you're trying to show something as true in a true-false question, you can't use this formula unless you were told if A is a non-singular matrix, right? However, I'm going to make it green for go. This formula can always be used. It doesn't matter whether or not A is singular or non-singular, and it doesn't matter whether the determinant of A is 0 or not 0. Because we're not dividing, you can always use it. Which means I like this one better. Okay? Okay. And we're at the bottom of the page. Well, we're pretty close to the bottom of the page, so let's go ahead and create a new page. And what we're going to do is we're going to grab our matrix and our cofactor matrix and make a copy of them on this new page because we're going to use them. There we go. So, what is, thank you, the adjunct of matrix A? It's going to be the 3 by 3 matrix. And what's the first column of this 3 by 3 matrix? 2, 12, 4. And what's the second column? And the third column? And it shows you that finding the inverse of a 3 by 3 is not that easy. The inverse of a 2 by 2 is going to be super simple. Okay? And that's because now we have to find the determinant of matrix A over here, right? And then I'll divide this matrix by the determinant and get the inverse right off the bat. So now we have to calculate the determinant of this matrix. Okay. Can't you just show up for me all the time? So 4, 2, negative 2. And 2, negative 1, 1. And come on. 3, negative 3, 2, negative 4. Negative 3, 2, negative 4. Okay, and now I'm faced with calculating this determinant. Right? But I can be pretty darn clever about calculating this determinant in ways that I'm not allowed to be clever when I just restrict it to row operations, because now I also have column operations. What's the first row operation I'm going to do? Can I add row 2 and row 3 to get a 0 beneath the 2? And subtract 2 times row 2 from row 1 to get a 0 above the 2? Does this make sense?
Isn't it negative 2, 2, not 2?
I don't know. 4, negative 2, 2. Okay. Thank you. Did I say it right? I don't know. We'll see in the recording, right? Are the rest of them okay? 2, negative 1, 1, negative 3, 2, negative 4. Okay. So now I'm going to add to row 1. I'm going to add 2 times row 2. And to row 2, I'm going to add row 3. And this is not an arrow, this is an equal sign, right? Because row operations don't change, type 3 row operations don't change the value of the determinant. So what do? I'm going to make a copy. But I'm changing 2 of the rows. Well, let's see. Okay, bless you. I'm adding 2 times row 2 to row 1. So 2 times negative 2 is negative 4, and negative 4 and 4 is 0. That was the whole point. And 2 times negative 1 is negative 2, and negative 2 plus 2 is 0. And 2 times 2 is 4, and 4 minus 3 is 1. Did everybody get that? I hope I got it right. You guys really do have to watch me on this. I'm going to make arithmetic mistakes, right? So keep on top of it. Now if I add row 3 to row 2, 2 minus 2, oh, I erased the wrong row. If I add row 3 to row 2, 2 minus 2 is 0, and 1 minus 1 is 0, and negative 4 minus 2 is minus 2, and now we have a problem. 2, 1, negative 4. How do I know the determinant's 0?
Singular?
What?
Singular?
How do I know that?
Because
It
two of the
has-
columns are free or
Yeah, one of the columns is free. Not both of them. One of the columns is free. One of the columns is 2 times the other column. One of the columns is a multiple of the other column, right? Which means that when I subtract 2 times column 2 from column 1, I'm going to get column of zeros and the determinant 0. So as soon as I found out that one column was a multiple of the other column, I know the determinant 0. So it's not invertible, right? So I can't calculate the inverse, but I can calculate the adjoint and the cofactor matrix, which means I can still use the green formula box, but not the one that's in the textbook. Yeah.
Can you explain the T51 adjoint A?
The adjunct you get from transposing the cofactor matrix. The adjunct is the cofactor matrix of A transpose. So I just transpose the cofactor matrix. Yeah.
Could you, what would happen if you transpose A and put the cofactor of that? Would that give you anything meaningful?
If it has an odd number of rows and columns, then it'd be okay. But if it's an even number, you're going to get minus signs in the wrong places because the sigmas will be backwards, right? Because if I transpose it, this one was positive. No, it would stay. I never thought about it. Let me think about it, okay? I don't want to say yes or no while I'm also thinking about everything else I'm thinking about.
I don't know if it's like, if you did, like, maybe a different thing that might be useful, I don't know.
So what he's asking is the cofactor of A transpose equal to the cofactor of A transpose? And the cofactor of A transpose would be this guy, right? Where the cofactors are Aij. And if I find, and that would be this guy, which is the adjunct. So yes, the cofactor matrix of A transpose is equal to the cofactor of A transposed. When I hit the button, be hit. Okay. The cofactor matrix of A transpose is the cofactor matrix of A transpose, because both of them give you, remember this was our notation for cofactors, and switching the indices is our notation for transpose. This is where, okay, so this is where the notation I tried to teach you last week comes in really handy. If you understand the notation, then it's really easy to answer his question. Is the cofactor of A transpose equal to the transpose of the cofactor matrix of A? And the answer is yes. And it was easy to show by just looking at, remember the cofactor matrix, oh, whoops. There. I left a T. Right? The cofactor matrix of A are these capital Aij's, right? Where the capital Aij was the cofactor, which is the segment times the determinant of the minor. Remember in our notes, the cofactor of element Aij is minus 1 to the I plus j, the segment, times the determinant of its minor. And we called this A, capital A, Ij, for matrix A. Right? And, okay, so, all right, this sounds like I'm showing off. I'm not showing off. I'm trying to impress upon something to you that's very important. I was a professional engineer for 25 years before returning to raising our kids and before returning to academia. During that time, I worked for Martin Marietta, Boeing, Texas Instruments, and I was a lead design engineer of Windows for 9 years for Microsoft. I'm not teaching you to do it differently than the way the book does because I think I know better. I'm doing it because working with other engineers in the field, this notation helped us solve the problems with as little pain as possible. This is the notation that we used, and this is the one that worked. Okay? If I deviate from the exact notation of the textbook, such as using the green formula instead of the dark squared formula, I'm doing it for a really good reason. And it's okay to ask. It's not going to hurt my feelings because I have that 25 years of confidence. I don't have to get my feelings hurt because you don't agree with me. I'm just going to go, well, you'll learn later. You'll grow up. Okay? But we have an entire committee that decided on this notation in this textbook and how we teach this course in those online notes. It wasn't just the work of one person, right? So give it some serious consideration. It's not random, okay? One of the ways that I have changed the way this class is taught is I bring up things that aren't in the textbook or aren't lectured about until later in the semester. I do that because when we get to later in the semester, you will have heard it 3 times, maybe 4 times. And the more often you hear it and the more often that I talk about it and lecture about it, the easier it's going to be when it becomes really important because it's in the textbook. This is not random. I am not jumping all over the place. I have planned out each of these steps and each of these lectures and each of those days of notes so that it works in a way that maximizes your ability to absorb this material in only 14 weeks. Okay? Let me bring up two other things that are really important to remember about this class. And the second one is, this class has a lot of vocabulary and a lot of new ideas. When you took Calc 1, what was the thing that was hard about Calc 1? What makes Calc 1 hard? And Calc 2 hard, for that matter? Does anybody think about it? Ever think, what is it that made Calc 1 and 2 so hard? Algebra and trig, right? If you remembered all your trig, wasn't Calc 2 a lot easier? But if you didn't remember trig really well, Calc 2 was a nightmare. And algebra, if you didn't remember your algebra, Calc 1 was very hard. But if you were really good at algebra, Calc 1 was limit, derivative, integral, done. Okay, that's all you really had to do in Calc 1. Okay, this course though, I'm bringing up things and talking about concepts for which you have no previous experience. So, it is normal to feel lost or drowning when you're in this class. This is why I don't care what your first test score grade is. What I care about is that it keeps improving. And the last test score, the comprehensive final exam. The other thing is, I am kind of prejudiced about one thing. I went to a college that taught very European method. I took a 4-hour final at the end of the semester, and that was my grade in every single course that I took. That's just the way that university taught. So, if I give you, we had quizzes and homeworks too, none of them counted. Okay? For you, they count. But they'll only count if they improve your grades. So, if your grades do this, then this is your grade at the end of the semester. If you have a high grade in the middle, and then you do this, and this one's not quite as high as this one, then I will average that one in order to bring your grade up. But I'm only going to average grades in during the semester if they improve your grade, not if they make it worse, okay? So it is normal to feel overwhelmed in this class because we have 14 weeks and we have a lot to cover. However, if you continue in STEM and you take classes in biomedical engineering or aerospace or fluid dynamics or physics or quantum dynamics or fields and waves, then you will be using this vector linear algebra over and over again, and your Calc 3, your vector calculus over and over again, and you will get better at it. When I was in my early 30s, I was still going, oh wait, I can do that in linear algebra. You are still going to be learning linear algebra for a while if you find yourself in a field that's going to be using it. And since it's 2022, the likelihood that you're going to find yourself in a field where you're using it is getting higher and higher and higher and not lower and lower and lower. When I was an undergraduate, very few non-math majors bothered to take linear algebra. Now practically every physicist, all physics majors take it, and practically every engineering major takes it, right? Computer science majors take it, right? There are even business majors now realizing that if they want to do machine learning, they have to take it, right? So the number of sections that we have of linear algebra went from 1 when I was an undergraduate to 5? So this is a pretty important course, but it's also full of ideas that weren't part of that curriculum. The whole reason why algebra is taught the way it is, no matter what country you're from, and the way that trigonometry is taught the way it is, so that you can learn Calc 1, 2, and 3. And the reason that algebra and trig and Calc 1, 2, or 3 are taught the way they are is so that we can teach you ordinary and partial differential equations. When you leave university, this is the third item. The things you're going to use are differential equations, because if you're an engineer or STEM and you are modeling, or business or finance, and you are modeling something in the real world that involves things that change from moment to moment or day to day or month to month or year to year, then it's a dynamical system. So we're going to use a differential equation to model it. Or we're going to use a statistical model, right? Machine learning, variance, covariance, Markov processes, Bayesian statistics, Bayesian graphs. How does the computer solve our statistics and our differential equations problems? Linear algebra. All of them. So in order to understand how the computer is solving the problem, you're going to have to understand linear algebra. In order to tell the computer in fluent if you're doing fluid dynamics in the engineering department here, you're going to have to write linear algebra equations. Right? That's just the way that Fluent works. Okay. So, I think that was worth the extra time. Now, the Laplace expansion. So we'll come down here.
If we're not supposed to use the Laplace expansion, why bother teaching?
One, it's in so many textbooks. That's a good question. Two, there's an exception, which we're going to talk about before the class is over. Yeah, I'm just going to teach you today, yes. There is an exception, okay? And you want to know what that exception is. You definitely want to know what that exception is because it's going to turn out to be really helpful. Okay. All right, the Laplace expansion. And if you think about it, we're going to base this in cross product. We're going to start with cross product to make the Laplace expansion as easy to understand as possible. When we calculate the cross product of two vectors, say the vector 3, 1, 2, okay, in calculus, angle brackets means I'm really a column vector. Right? It was just an easy way for me to write a column vector without having to get out the straight line drawer and draw a column vector. Okay. But I don't like the 2. Cross 1, negative 1, 0. Let's make it easy. And the way that we do this is we create a matrix. And this matrix is a 3 by 3 matrix, which when you watch the first and second video on cross products, you'll realize that, isn't I hat a vector, not a scalar? Why does this work? It works because cross product is really, if you take Calc 4, yes, we do have a Calc 4, a tensor product. Yeah, it's just not offered very often because students don't sign up for it. But yeah, Calc 4 is tensor calculus, which is what you need for quantum mechanics. Right?
Thank you for letting
There's a
me know
Calc 4.
class to avoid.
There's a Calc 4. Oh, it's awesome. Cross product is actually a tensor product. Okay? And if you take tensor algebra or tensor calculus, you're going to find that when you calculate the cross product of 2 3 by 1 vectors, you get 9 tensors, 9 elements to your tensor. It's just that 6 of them are zeros. So the 3 of them that aren't 0, you consider to be the coefficients for I, j, and k. And you call it a vector. Okay, why does it work? Well, because the geometry where the vector is perpendicular using the right-hand rule, and the length of the vector is equal to the area of the parallelogram, just happens to work. Originally, it was the length of A times the length of B times sine theta. It was just easier to say it's A cross B. Okay? And so what we do is we put the first vector and the second vector. And I wrote it this way on purpose because this is not the way I do it. Because to me, they're all column vectors. So I write, but we learned yesterday, or Tuesday, that the determinant of A transpose was equal to the determinant of A. So it didn't matter which way we wrote it. We were still going to get the same answer. So it doesn't matter which way you write it. And that the answer is, well, what's the sigmoid for I hat? Positive. So you get I hat times the determinant of its minor. And what's the sigmoid for j hat? Minus the j hat times the determinant of its minor. And the sigmoid for k hat is positive again, times the determinant of its minor. So we end up with the vector 0 minus the negative 2 is 2 I hat. And we get 0 minus 2 minus minus 2 is a plus 2 j hat. And negative 3 plus 1 is a negative 2 minus 2 k hat. Or the column vector 2, 2, negative 2. Is that what everybody else got? Did I make a mistake when I did my determinants? Okay. So this is all good. Okay. Now, can we write Laplace's generic? I guess I need a new page because I'm at the bottom.
Can you double check the one for K? I'm not sure about that.
Yeah. Yeah, you were right. Not a very nice K. There, I like that one better.
Isn't the determinant of that matrix -4?
That matrix -4 isn't enough, specific
I'm
enough for me to
sorry.
figure it out.
I'm sorry. The
-3 minus 1, the third one?
Yes.
Okay.
-4. I'm sorry.
Yeah. Negative, it's not 3 minus 1, it's negative, oh, I put -3 plus 1. It's -3 minus 1. Thank you. Excellent.
I was just wondering.
It's like my youngest brother is blind. And when my kids were little, you know, he would ask them, well, where's the remote? Over there. Not very helpful. They figured it out. They figured it out. What's weirder is that he's younger than some of my kids, but older than others. So he was right in the middle. So they played a lot together. Okay. In fact, they made up a basketball team. I was actually pretty proud of my kids because they spent like 10 years playing basketball with somebody who can't see on the team. And they accommodated it just fine. They figured out ways for him to play the game, and that they would yell at him and tell him this, so they knew that passing the ball this direction, and he would just do this and cover the ball. They would tell him where to shoot. We never did I always wanted to put something that made noise where the goal was, but I never got around to doing it. They didn't need it. Okay. Which was pretty cool, I thought. Where are we now? The Laplace expansion. The determinant of A is you pick a row or a column. It doesn't matter what row or column you pick. And that's the weird part about the Laplace expansion. You get the exact same answer no matter what column or row you pick. So you pick one. We're going to call it L. And you add from k equal 1 to n. A, if we pick a row, LK times the determinant, the sigma times determinant's minor. In other words, it's cofactor. If we pick a row instead of a column, no, if we pick a column instead of a row, it'll be so we can figure out the determinant of a 5 by 5. It's the sum of 5 factors times their cofactors, right? The factor is the element of the matrix. The first one, this is the element of the matrix. This is the factor. And then, of course, we have been studying for the last hour now. This is the cofactor. So that's exactly what we did when we calculated cross product up here. We multiplied I times the sigma times the determinant of its minor. In other words, I times its cofactor. Plus j times its cofactor, but the cofactor of j was the negative of the determinant of its minor. Plus k times its cofactor. And that was the positive determinant of its minor, yeah.
Every single time I've learned this class, the cross product back in Calc 3, they never explained that it's actually a column vector.
I know.
It was so frustrating because I hated drawing the horizontal version of that matrix. The
Right.
vertical version that you have, the column version, is so much easier to understand.
Yeah, the column version makes sense to me too. That's why I always use it. But the row version will still give you the right answer.
Yeah, but it's much more
And now we know why. The determinant of the matrix and its transpose is going to be the same thing.
Yeah.
And we know all the properties of determinants, and now we know the Laplace expansion. So we could use this to calculate the determinant of a 7 by 7. After all, it would be the sum of 7 factors times their 7 cofactors. So that would be 6 by 6 determinants. And each one of those would be 6 5 by 5. So that's 42 5 by 5s. And that would be 210 4 by 4s. And that would be 820 3 by 3s, or 2,430 2 by 2s. And yet, people will do that, and it takes up half the class period. You know, you only get an hour and 15 minutes to take the test. You don't want to spend 70 minutes calculating the one problem. It's just silly. And I'll give you a hint. I design the determinant so that you can get it into upper triangular form in like 4 steps. That way, it doubly penalizes people who try to use the Laplace expansion to figure it out. Okay, yes.
Can you remind me, so to get the determinant, you put it in upper triangular form, you take the diagonal, the
Product of the diagonal elements, yes.
Does lower triangular form work too? Or
Does
do you
what?
have to does lower triangular form work?
Just as easily, yep.
Okay.
Just gotta do some different stuff, probably, just slightly different row operators.
Yeah.
Yeah, you're just performing different row operations and or column operations. So now I want you to calculate the determinant of this matrix in your head. Now I want you to use mental arithmetic to calculate the determinant. And this will illustrate the exception to using the Laplace expansion. I claim the determinant 6. Does anybody see why it's an exception?
The zeros.
There's a column with only one non-zero entry. That's the exception. Because after all, if we use the first column, it's 0 times the determinant of its minor minus 1 times the determinant of its minor, which we need because we have the 1, which is 2, 5, 4, 7, plus 0 times the determinant of its minor. And I'm not even going to write them down because I'm multiplying them by 0. Right? Does everybody see why I'm not bothering to write down the other matrices, sub-matrices? And so I got 14 minus 20, which is negative 6, and negative 6 is 6. Okay, let's try that again. Let's write a 3 by 3. What is, what's the determinant? I claim it's negative 20. I'll get it right?
I think so.
You could even write on the paper and if I want to be really formal and show all my work, I would write minus 0 times the determinant of its minor plus, remember the checkerboard. The first zero, this 0 has a segment of negative, right?
Wouldn't it be minus 19?
Yeah.
Well, let me see. You might be right. Plus 4 times the determinant of its minor, and I get 7 minus 12. Isn't that negative 5?
Yeah.
Oh, okay.
Plus 0 times the determinant of its minor. And so I get negative 20. Did I say negative 20?
Yeah, that's what you said.
Okay. This is the exception. So if you used row and or column operations in order to get one row or column to have all zeros with only one non-zero entry, you could use the Laplace expansion to make it a smaller determinant, right? Yeah.
So like if you have 2 zeros, even if they were column, even if it were a column or row, it doesn't really matter. That's just a really shortcut.
Yeah.
Potentially
All right, so let's go to our notes. Here's all the stuff I was talking about, and here's expanding the determinant using the sigma and the factors and the cofactors. Okay, and here's getting the determinant using a combination of row operations and the Laplace expansion. After all, if I subtract 2 times column 2 from column 1, right? 4 minus 4 is 0, 2 minus a negative 2 is 4, and 2 minus 2 is 0. And I end up with a column with 2 zeros and a 4. So it will be 0 times the determinant of its minor, minus 4 times the determinant of its minor, plus 0 times the determinant of its minor. In other words, 20. So let's look at some of these exercises. And you're supposed to do these in your head. What's the determinant of number 1? 6 plus 8. Does everybody see it? 6 plus 8. Okay. What about this one? Be careful.
Positive, yeah.
Because the sigma's negative.
Yeah.
It's positive 2, isn't it? Let's check. Okay. What about this one here? Negative 27? Okay. What about this one here?
0.
What?
0.
You have 2 identical columns, don't you?
Yeah.
So it's 0. So you just write equals 0. There are 2, the first and the third column are equal. What about this one?
Would it be 0?
No?
No, it would be minus 8, right? 4 minus.
Well, what's 4 minus 16?
No, minus 12.
And negative 12 times 4 is negative 48, and the segment's negative, so it's plus 48. Okay, it's... Wow, it's off the end of the page. Sorry, misprint. What about this one? Okay, I'm going to take a picture of it. And remember, I'm recording. Yeah, I know. That's why I'm taking a picture of it. And we're at the bottom of a page? Maybe not. No, we're not. It's a really tiny picture. Okay, here we go. And you see that 1 right there? Is that a 1 or a negative 1? Is this a 1 or a negative 1? The sigma's negative, right? So that's a negative 1. Times the determinant of its minor. All right, so now you've got a 3 by 3. Would that have been the wisest choice? Let's see. No, that's not the wisest choice. Yeah, the 2. So it's plus, minus, plus, minus, plus. So it's a plus 2 times the determinant of its minor. Okay, now, this 3 by 3 that has rows negative 3, 1, 1, 0, 0, and 2, negative 3, negative 4, what's the cofactor? The factor is a 1, but the sigma is negative, right? And from that 3 by 3, we're going to remove its row and column. And now what are we left with? 12 plus 3 is 15.
Times the original 2 times the 1.
Okay. What about this one? What's the determinant? 0. It has a column of zeros. What about this one? Has a row of zeros. What about this one?
0.
Why?
Because one is a linear transformation of the other. It's 4.
Well, a linear combination of the other, right.
A linear-
Right.
one
The
is
first
a-
row, the first row is the negative of the second row, and, is there an and to that? Nah, that's enough.
The third row is 1/4 of the second row.
What about this one? This is an interesting one. What about, oh, see the scroll bar over here that they made for the missing number up there at the top, 48? So we use Jupyter Notebook. We create a notebook and then export it as an HTML file. Convert it to an HTML file. That's how we author these. Okay, what about this one? Well, the -1, its sigma is positive, so that's a -1. Let's go ahead and take a picture, because we're getting at the bottom. We can take our time. Is there any rule or reason to the size of the image after you copy it? I can't figure it out. It's like Windows has this secret way of calculating it now. Okay, so we have a -1. Remember, this only works because the other numbers are zeros. What about the -2? Its sigma is plus, minus, plus, minus, plus, right? So it's a positive -2. And you have to recalculate the pluses and minuses from the minor that you now have. And finally, what's the third factor?
3 plus 8 would be 11.
Yeah, 3 plus 8. So we get 11 times 2. I'll save it. And hopefully I got the right answer here. Let's see if we get 22. Complex valued matrices of determinants. You know this was going to come eventually, right? We're doing algebra eventually. We have complex numbers. Okay. Does everybody remember what the conjugate of a number is? The conjugate of a complex number, a plus bi, is a minus bi. So the conjugate of 1 minus 2i is 1 plus 2i. And the conjugate of 2 minus 3i is 2 plus 3i. And there are 9 of them. All right? Instead of transpose, when we have complex valued matrices, and we absolutely need this if we're going to be doing electrical, quantum mechanics, or integrated circuit design, because it's quantum mechanical in nature, then we need the Hermitian. The Hermitian is the conjugate transpose, not just transpose, but the conjugate of all the elements that you transposed. So the conjugate transpose is first column will be 1 plus 2i, 2 minus 3i, 3 minus I, which you see here. And the second column of the Hermitian will be 4 plus I, 5 minus 2i, 6 plus 3i. So you have to do both. You have to conjugate every element in your matrix, and you have to transpose the matrix. The thing is, doesn't bar over the top mean conjugate? But we use bar over the top to mean it's a vector, right? How are we going to fix this? I'm never going to use, in my notation, bar over the top to mean conjugate. Instead, it'll be Hermitian, because what's the transpose of a 1 by 1? Yeah, it's nothing. It's the same number. It's a scalar. So if I write scalar Hermitian, like I did down here, I mean it's conjugate transpose, but the transpose of a scalar is just the scalar, so it's the conjugate. I will always write, and physicists use the splat, right? Why splat? Because it's so much easier to say than asterisk, and it has a lot fewer syllables. So, by the way, the exclamation point I call bang, because computer sciences use bang rather than exclamation point, again, to shorten the number of syllables and make it also easier to say. Okay, so the conjugate of the sum of two complex numbers is the sum of the conjugations, and they commute. The product of the conjugate of the product of two complex numbers is the product of the conjugates. That means that the same work for quotients, and obviously the conjugate of the conjugate is the original number. So in my notes, you will see the splat and the h, even if we're talking about a scalar. Because in my notes, I can't write in bold, so the bar over the top means I'm a vector, not complex conjugation. Well, that means the same. You learned these rules back in algebra class. So in linear algebra class, it turns out, thank goodness, that the rules are exactly the same. A plus B, the Hermitian of the sum of two matrices is the sum of the Hermitians, and it commutes. But remember, transpose reverses the order of the multiplication. So if you want to bring conjugate transpose inside the parentheses, you have to reverse the order of the multiplication because we're transposing. But of course, that doesn't work with scalars. And the Hermitian of the Hermitian is the original matrix. Because the conjugate of the conjugate is the original number, and the transpose of the transpose is the original matrix. So the Hermitian of the Hermitian is the original matrix. What if a number is equal to its conjugate? Well, that means that B has to be 0, right? If A plus BI equals A minus BI, then B has to be 0. What about a matrix that is equal to its own Hermitian? Well, that means the diagonal elements have to be real numbers, right? Because when you conjugate them, they stay in place and they're equal to their own conjugate. This matrix is Hermitian because it's equal to its own Hermitian matrix. Remember that when a matrix equals its own transpose, we call the matrix symmetric. If a matrix is equal to its own Hermitian, we call it a Hermitian matrix. Okay. It turns out that the determinant of the conjugate of a matrix is the conjugate of the determinant. That shouldn't be too hard. Just write out the Laplace expansion, right? And that so you can write it using DET or using the vertical bars. And since the determinant of the transpose is equal to the determinant of the original matrix, the determinant of the Hermitian is equal to the conjugate of the determinant, right? The transpose part doesn't change the value of the determinant, but the complex conjugation part changes the value of the determinant. Now, another thing you should be aware of is that a lot of modern physics books, meaning Physics 3 and Physics 4 books, use what's called the dagger. It's not really a plus sign, and if you see it printed in a book, it really does look like a little bitty dagger to mean Hermitian or complex conjugate transpose. So instead of using the capital H or writing it out this way, they put the little dagger there to mean complex conjugate transpose. So this is the... I can't draw little daggers very well. However,
That's the notation.
we have the sum total of all human knowledge available to us, so physics, dagger, Hermitian. The complex, see what the dagger looks like? It really does look like a little bitty 15th century, 16th century dagger. European. Okay? And I don't know where the dagger comes from. Obviously, it was a very famous physicist, right? Probably Dirac. Because he had his own notation for everything. What's this the notation for? Dot product. He just couldn't use dot product. So he calls this a bra and this a ket for, brackets. I don't know what was going on in the early 20th century, but so they use this dagger all the time. So you have to be aware that that can happen. You could pick up a textbook, especially a physics textbook. If you see the dagger in a matrix or vector, it means complex conjugate transpose. I'll always use H. And if it's a scalar, I might use the splat. You there? It kind of gives you the hint that it's complex conjugate transpose. Okay. Any questions before we go? Thank you very much. Have a wonderful day. Keep posting things. Post things online. You know, you need what? What is 2 times 14? 28? 2 times 13? 26? All you need are 26 posts that aren't me too or asking the same question that 3 other people already asked, right? And that's a test score of an A. I don't think anybody doesn't want an A averaged into their grade, right? So use the online discussion board. Read some of the other questions and answers that are up there because there are probably some good answers up there, some good questions. Thank you very much.